Thanks for this introduction, Asaf, and also thanks to Ronen, Eldan, and Elizabeth Werner for inviting me to speak here in this winter school, in this trimester, which is in memory of Elizabeth Meckes, as we heard yesterday. I admire that a lot. So I'm going to talk indeed about the isoperimetric problem on Yuansi Chen's work on the KLS conjecture. The KLS conjecture is a question about the isoperimetric inequality in high-dimensional convex sets and log-concave measures, as Asaf said. 6.5 weeks ago, Yuansi Chen uploaded a preprint to the archive, which represents significant progress towards this conjecture. And my goal in these 3 lectures is to discuss this progress, this recent progress, and the ideas on which it builds. So my plan is as follows. So today there will be more of a survey or background on the KLS conjecture. Can you see what I'm writing? I think you do, right?
Yes.
Thank you.
Yes.
Thank you. Okay, so there's a background on the KLS conjecture. Tomorrow it will be about Eldan's stochastic localization method and the version of Lee and Van Pala of this method. And on Thursday, the lecture will be about third moments of log-concave measures along a certain dynamics. But let's begin with this conjecture, which is an isoperimetric problem. So as in the lectures of Joe Niemann, I'll begin with isoperimetry. Okay, so let's do it in a slightly general setting. So we have, assume that we have a metric space, XD. And suppose that we have a Borel measure on this metric space, mu. Okay, so this is a measure, and Borel measure, and this is a metric space. So this is called the measure metric space. Okay, so this means that you can measure distances between points, and you can measure sizes, measures of sets. Okay, so if you have a subset A in X measurable, then we have its measure, which is mu of A. But we also have its boundary measure. Its boundary measure was defined yesterday in John Niemann's lecture. He used the lower outer term in consequently, which is what I'm going to use too. So mu plus of A is the lim if, when epsilon goes to 0, of the measure of the epsilon neighborhood of A. So we have a metric, we can take neighborhoods, minus mu of A over epsilon. Okay, where A plus epsilon is the set of all points, let's call it X in A, X in X, so that the distance from X to A is at most epsilon. Now, please forgive me for slightly changing the notation. So I'm a bit used to writing this as mu plus of the boundary of A, although it's not really a function of the boundary. Just this reminds me that this is a boundary measure. I see the boundary here. So I hope that it's okay with you that I use also this notation because I'm more used to it. Okay, so what is the meaning of the boundary measure? So the boundary measure, we do the following. So this is X. We have our set A, maybe this is A. And I'm going to take its epsilon neighborhood, which is a thin layer about its boundary. I'm going to take this measure divided by epsilon. Okay, so this is the boundary measure. And an example that was an exercise yesterday is the case where your space, for example, is so X is some open set in Rn. Let's say maybe with a smooth boundary, maybe some regularity. And your measure mu, so d mu to dx, mu is a density. The measure is as density p, where p is some function from omega to r, or to it's a density, so it's a positive thing. Say it's continuous up to the boundary, or let's say even smooth or something. Okay, let's say continuous up to the boundary. And then if you have a set A, so under some, if A is regular, so for subset A, if it's the boundary is regular, well, under regularity, so the boundary is smooth, I think. This was the assumption in Hausdorff. What is the boundary measure of A? Well, since you take a small neighborhood topological boundary and you divide by the width, then you're going to get just the integral over the boundary of A of this density P. Okay, this is an example. Okay, so what is the isoperimetric problem in this generality? So the idea is that you fix a certain number T, and you look on all sets whose measure is T, and you try to look at the infimum of the boundary measure. Okay, so that's the goal. You want to find a set that minimizes the surface area or the weighted surface area or the boundary measure for a given volume. Okay, and you want to find the minimizer and the value. This is the isoperimetric problem. Let me show you examples where we have exact solution. So for example, if your space is Rn and the metric is the Euclidean metric and the measure is the big measure, then you know that both minimize surface area. If you're on the sphere or the hyperbolic space, again, both minimize. There are also other cases where it is known. You can take in a half space in Rn, half bolts minimize. That's there's some story about some princess in the Princess Dido in the Greek mythology about half space. You can take a Euclidean ball or a ball in some space. Let me also add example which is not completely okay. So the Hamming cube, I put quotation marks. The Hamming cube, 0, 1 to the n. So it's not completely okay because the boundary measure is a different definition. When you look at the Hamming cube, it's a graph, it's a combinatorial object. You don't let epsilon tend to 0, you just take epsilon equals 1. You just take all vertices that are adjacent to your set, but it's still of the same spirit. An example which is more relevant to us is the example that is the subject of the lectures by Joe, which is the Gaussian case. Okay, so you take Rn with the Euclidean metric, and gamma n is the standard Gaussian measure in Rn. Okay, so the density, you know, I write it, but I guess you all know it. So that's the density, right? And that's an important example in convexity. Okay, so these examples, the list is not, this is not a complete list, there are more examples, but these examples are either highly symmetric or at least highly with very good structure. There are also other cases where exact solution is known, which are not completely symmetrical structure. So in 2 dimensions.
Sorry, wrong power in exponent.
Is there any question?
It should be second power in the exponent.
Thank you. Thank you. Yeah, you're right. Thank you, Yolanda. Yeah. Very good. Thanks. By the way, you're most welcome to stomp in and make corrections, definitely, and even ask questions during the lectures. Thank you, Yolanda. Okay, so in 2 dimensions, if your set, if X is a convex set, convex domain Rn, and the metric is Euclidean, and the measure is Lebesgue, so convex body, convex shape, and U is Lebesgue, then it is known what is the solution. So let me draw some polygon. I think it looks like a pentagon. Very good. Then the extremal set is always an arc of a circle, a single arc. Let me emphasize it. By convexity, it's a single arc of a circle or a straight line. So that's the boundary of the minimizer. Straight line segment, you write maybe. If it's an arc, it's a segment. Okay, and also it meets the boundary orthogonally. So this is the type of objects that are relevant in 2 dimensions for convex pointer. So that's very good because the space of all circles is 3-dimensional, and you have 3 constraints. The area is T, and you have 2 right angles, so kind of you're in good shape. 3 constraints, 3 equations, 3 variables, so you can say something about the minimizer. However, if you are in higher dimension, it's much more difficult, and you don't know so many things you can say. So you should be satisfied if you have some non-trivial approximate solutions. Okay, so in mathematics, you have in certain fields some approximate solution to a isoperimetric problem. In combinatorics, you have expander graphs. You have examples in geometric group theory. You have examples in Riemannian geometry. But what we care is convexity. Convexity in Euclidean space. Okay, so from now on, so our space X will always be either Rn itself or at least a convex set in Rn. Say open and convex. Our metric D will be Euclidean. Now, what about mu? So mu, so either mu is the uniform measure. So if K is bounded, is the uniform probability measure. Okay, or else, or more generally, it can be a log-concave measure. Always a probability. So it's a probability measure with a log-concave density. With density P, let's say on Rn, which is log-concave. So log-concave, this means that P of lambda x plus 1 minus lambda y is at least P of x to the lambda times P of y to the 1 minus lambda for any x, y, lambda. Okay, so for example, the constant function on a convex set is log-concave, and also other measures like the Gaussian measures log-concave. Okay, and if you don't remember the difference between concave and convex, so P is E2 minus rho. Okay, where rho is convex. Rho is convex means that the Hessian of rho is positive definite. Okay, so this is, so rho kind of looks maybe like this. This is rho. So P is more like this, like a Gaussian. Okay. Now, question: is convexity relevant at all to isoperimetry? So why would we restrict it to convex sets? So the answer, I think, is yes. And this goes back to the 19th century. So there is a complete detailed proof by Poincaré of the Poincaré inequality for which gives us the spectral gap for two-dimensional convex sets in R3. But also, let me show you another example for the relevance of convexity to isoperimetry, which is a theorem due to Sternberg and Zumbrunn. In the convex body case, from 99, in the convex body case, and to Emanuel Millman in the general case, the log-concave, so in the general log-concave case. So this theorem says that the isoperimetric profile is concave. So under the above assumptions, what does it mean? Let's define I of t. So I already wrote it, but let me repeat. I of t, this is the profile. It's the infimum of the boundary measure of a set, where this even goes over all measurable subsets for which it's fine in Rn, yeah, in Rn probably, for which the measure is measure is t. Okay, so this is a function. So if mu is a probability measure, that's a function of the interval 0, 1. Okay, this is a function between 0 and 1. And what the theorem tells us, this is a concave function. Okay, it is also symmetric about 1/2. This was also true. It is also symmetric about 1/2 because you can take the complement of the set. Okay, so this is a nice statement. It tells you that if you join two sets, then the total boundary cannot be optimal because so this implies that the optimization is connected. If you look at two separate systems and you look at their union, this loses in the competition with respect to the minimizer. Another good thing about this concavity is that it's a positive function, so its value here is some number. It does not have to reach 1, by the way. Maybe I'll draw it like it can reach, it could be, yeah. So in some cases, it's okay. It usually reaches 0, but okay. In some cases, it can do it positive. Anyway, it is above this function. So if you take the linear, a concave function lies above a linear function, above a chord, above its chords, and therefore, what we can say is that this function I of t is at least this little purple triangle. So, and this equals twice I of 1/2 times the minimum of t and 1 minus t. Okay, or if you want, so the corollary would be that for any subset A in Rn, its boundary measure, so you know it's at least I of the measure of the set, so it's at least this number here, the measure of A, the minimum of the measure of A and its complement. This is 1 minus the measure of A, it's a probability measure. Okay, this is a nice property that follows from convexity. Now let's give this quantity a more respectable name. So this is the isoperimetric constant or the Chigger constant. So definition, the isoperimetric constant or Chigger constant of mu is this, well, it's actually, okay, it's really 2 I of 1/2, but it's the infimum over all sets in Rn of the boundary measure of the set over the ratio of the minimum of A and its complement, 1 minus. Okay, and we know it is attained for sets of 1 measurement 1/2. Okay, very good. So that's the isoperimetric constant of a measure mu. Now we are interested in convex sets. So, well, how would you partition a convex set into 2 parts of equal mass? What's the best way to do it? So you want to minimize the interface, right? You have your set. The measure says the uniform measure in the convex set. You have you want to find the set A such that it minimizes the with a given say measure 1/2 1/2, and you want to minimize the say it's okay. Let's ignore my picture. Okay, well, let me make it more. So do 1/2 and 1/2, and I want to minimize the interface, this part. How would you do that? Well, one possible way is to use a bisection by hyperplane, right? I mean, convex sets interact nicely with hyperplane somehow, and so you would imagine that maybe it's not that a bad idea to intersect with the hyperplane. And this is the KLS conjecture. Kannan-Lovasz-Simonovits. Simonovits conjecture from 95. So what they claim is that if you take a half space, okay, it will not be the optimal solution, but to give you a very good approximate solution. Okay, that the conjecture is that up to a constant bisected by a hyperplane. So in other words, there exists some universal constant C, such that for any n and any mu in Rn log-concave, this isoperimetric constant psi of mu, you know that okay, it's at least what you get when you only take half spaces.
How universal is your constant?
1/75. This is universal. That's the conjecture. Okay, so you should prove it with 1/75. If you do 1/76, it's still okay. So, okay, Tomer? So,
yeah, okay.
You want to minimize the boundary of h over this minimum of same thing as before, mu of h times 1 minus mu of h. Okay, so clearly the constant cannot be larger than 1 because this infimum is larger. I mean, formally, it's an infimum over a smaller set, so it's larger. It's under the probability constant, but the conjecture is that you don't lose much when you take half spaces. Okay, so just a remark. I mean, many remarks. So first of all, it's much easier. Let's call it star. So it is much easier to compute the infimum over half spaces. Okay, why? Because of the relation to the covariance matrix. So mu is log-concave, it has moments of all orders. In particular, you can consider its covariance matrix. Okay, so Cij is the integral of xi xj d mu minus the xi xj. So that's the covariant matrix. Okay, and as it turns out, the right-hand side here, the right-hand side of star is up to constant, up to universal constant, multiplicative constant, is just 1 over the operator norm, root of the operator norm of the covariance matrix. Okay, why is that true? Okay, wait, first of all, so this means that KLS is the question, is equivalent to say to the inquiry that psi of mu is at least a constant over the covariance matrix of mu square root of it. Why is it true? So this is a result of, why is it true? So why do we have this covariance and hyperintersection? This is because this is a result of Hensley from 80, and it is in the convex set case, even symmetric, and that is in the general case in 99. What they proved is that for any unit vector theta, Sn minus 1 is the unit sphere, all unit vectors. If I look at the square root of the covariance matrix of mu in direction theta, and I multiply it by the boundary measure, by the supremum, or by the ones of the boundary measure of any half space, all of spaces parallel orthogonal to theta. This thing is between I think I remember the constant. I think it's 1 over root of 12 and root of 2, but to be honest, I mean, I'll put was constants. Okay, so the covariance, so if this is your convex set, the covariance, the root is the variance in this direction. This is kind of the scale in which it lives in this direction. This is the direction of theta. And what it says is that if you look at on the maximal section in this direction, it will be roughly 1 over the covariance. And moreover, if you take the one which you can find ones that divide your set into a ratio which is roughly half and half, say 1 over e to each side, which reaches this bound. Okay, so that's this is not. This follows. I will not prove this. It's a classical thing. I prove it in my class. This follows from Prekopa-Lendler. I mean, at least it reduced. I mean, well, okay, not really. Prekopa-Lendler reduces matters to one-dimensional log-concave measures. To 1D log-concave functions, and it's because if you look at the function, let me call it p of t, okay, or let's say p0 of t, which is just the integral of p on the hyperplane x theta equals t, it is log-concave, and everything is expressed in this function in terms of this function. So this is why it is true. Okay, so this is the first remark. So it's about basically the covariance matrix. A second remark is that if it's determined by the covariance matrix, and the covariance is something that you just some kind of you can change it by a linear transformation, then let's normalize. Okay, so we can normalize. And if the covariance of mu is identity, if you apply linear map and got something of identity covariance, and the bias under the origin, okay, and well, integral of x d mu of x is 0, then we say that mu is isotropic or normalized. Okay, or normalized. So this is just a normalization condition by a linear map. Okay, and therefore the KLS conjecture, what it tells us is that actually it's equivalent, if you think about it, to saying that for any mu isotropic and log-concave, psi of mu is at least a universal constant. Okay, so why is it equivalent? If you scale, you can see that the worst case is if the covariance is, if you look at this formulation. So this formulation didn't quite prove. I just said it follows from classical things. Some result about convexity that you can project one dimension and understand what's going on. But this is, I think, an exercise. If you scale everything, you can think how the surface area changes, and you can understand that this reduces to the isotropic case. Okay, so now that is the KLS conjecture. Oh wow, I see I have 6 questions in the chat. Wow, is it still relevant? Should I answer this question, or is it really is different set considered closed? I think the answer is no, but as long as okay, there was some. I think okay. I will just other result in the non-Euclidean metric case. So that's a very interesting question. So if you look, I think, for example, you could formulate the KLS conjecture in the spherical case or the hyperbolic case. You have this, half spaces also there. But if you take very tiny objects, then you go back to the Euclidean case. So maybe first solve completely the usual Euclidean case and then continue further. Okay. This was about the plane. Yeah. Okay, Galina. Yeah. So in 2 dimensions, the minimizer is always so
what I was asking is what happens if you include the boundary? If you imagine that your convex set is
problem. This is the different boundary. This we did not discuss. This is a different problem.
Okay.
Okay. So now let's look at the results of Chen. So let's look at the worst things that you know in Rn. So difference of psi of mu, where mu in Rn is log-concave and isotropic. Okay, that's psi n. So the KLS conjecture says that psi n is at least a constant. And a theorem by Chen from 2020 says that for any, so it is it's not really bounded, but it goes slower than any polynomial. So for any epsilon which is positive, there exists some constant c epsilon such that psi n is at least c epsilon over n to the epsilon. Okay, so it decays very slowly. And if you optimize over epsilon, what you get is that psi n is larger than constant. Everything is universal constant. Don't worry, nothing depends on it. Root of log n times log n. Okay, times right, root log n here. Okay, so this is the result of Yuansi Chen. Okay, what were the early results? So first of all, Kannan-Lovasz-Simonovits used a technique which was called convex localization or needle decompositions. What they prove is that so KLS in 95 said that psi n is larger than 1 over root of 1 over n to 0.5. Okay, this notation brings up to a constant. And this is the first boundary. It doesn't really kind of capture the high dimensional nature of the object. So it's a bound actually by the second moment, that's vector over x squared. Bourgain used the same method in 07 and got a bound which was in terms of certain parameters. It was n to 0.25 times root of a parameter called sigma n. Sigma n is a certain parameter, which is called the thin shell parameter. The thin shell parameter, just for export, I'll say that this is the variance, this is root of the variance of the Euclidean norm of random vector x if x is log-concave and isotropic. So the maximum thing in Rn. And now, the relation to thin shell enabled to have some bounds using Bob-Kov's estimate. So first of all, in 2007, it was proven, I think, something like 0.46. This was my result. Then Fleury in 2009 got n2 minus 7/16 in this formulation. Then Guédon and Millman, Olivier Guédon and Emmanuel Millman, got in this formulation minus 5/12. So these things are improving. Then came a new method, stochastic localization by Bourgain and Eldan. And Eldan got n2 minus 1/3. Okay, so this is an exercise in arithmetic to verify that these are indeed improvements. And Lee and Vempala, they got a very clean exponent. They got 1/4. And at the time, some people thought that maybe this is it. Maybe this is the right bound. So I'll comment on it in a second. Okay, but now it's not the case, and we know that the bound is much better. So it's decay is slower than a power law. It's almost bounded. What are the applications of the KLS conjecture? So first of all, we have a Bourgain slicing problem, which is still open. So the question is whether, so is it true that, does there exist a constant such that for any K in Rn convex volume 1, there exists a hyperplane H with lower bound, which is at least universal constant. This is not known. If you write 1/Ln for the best thing that you can put here, this is the best in Rn, then Bourgain proved in 91 that this is at least n2/4. Actually, I remove the quarter a bit later. The log n, I wish I would remove the quarter as the log n. And some years later, Eldan and myself, we proved that Ln is at most 1/Pcn, and Bourgain and Guillen proved that Ln is smaller. So this is later, but it was announced before. Exponential of 0.sin squared. Anyway, if you look at this bound, you kind of see that the n/4 is what we would expect somehow. I mean, it at least recovers the best known result. And well, perhaps this exponent was a bit in our mind, and for 30 years, there were 3 different points of view that led to this 1/4. Maybe it was kind of a barrier that we were freed from by Yuansi Chen, kind of untied the Gordian knot, if you want. Okay, second application is for approximately Gaussian marginals. Okay, so now we know that this isotropic constant is at least n to an epsilon. Okay, so if x is log-concave isotropic in Rn, then there is a theorem, this convex CLT, convex central limit theorem, which says that for most unit vector theta in the sphere, the Kolmogorov distance of x theta and standard Gaussian is most C over n to the alpha, where C and alpha are universal constant. This is standard Gaussian, and this is the Kolmogorov distance. And this is standard Gaussian. And if you use the result of Bobkov, this Kolmogorov distance, this is this, okay. If you use the result of Bobkov, Chistiakov, and Goethe from 19 plus Chen's bound, then what you get is that for any epsilon, you can take alpha, which is 1 minus epsilon. Okay, so that's pretty good rate of convergence. It's, if you look, it's better than Berry-Sin. But Berry-Sin is 1 over square root of n, but Berry-Sin is about specific direction. And here it's about a random direction. A third application is Chigers inequality. Okay, I guess that many people know that. I think it was mentioned in lectures yesterday. So lambda mu is at least psi mu square over 4. Okay, this is all true without any convexity assumption. It's general inequality, where lambda mu is the Poincare constant, spectral gap. So it's the best constant in the inequality, in the Poincare inequality. The Poincare inequality says that for any phi, smooth test function, say local Lipschitz, the variance of phi times lambda. So the best lambda, that's the best lambda is the Poincare constant. The maximal lambda is smaller than the integral of grad phi squared mu. Okay, where variance of phi is the integral of phi squared mu and the integral of phi d mu squared. Okay, I see more questions in the chat. Let me guess without looking. What's the Kolmogorov distance? I was hesitant, so let me write it first. So d of 2 random variables. Let me put it in another color. Kolmogorov distance. So d of yz is the supremum over t in R for the difference of the probabilities. Now let me see if I was wrong or right. Bourgain works measure by measure while Eldan Klartag. Yes, this is true. Okay. Yeah, so that's the Poincare constant, lambda mu. And once you know that you have this spectral gap, then you know that certain semigroups, like you know that the heat semigroup with normal boundary condition has a spectral gap. So this means that the heat semigroup is mixing fast. So the relaxation time, the time to reach the equilibrium, is roughly 1 over the spectral gap. Okay, so you know that certain Markov processes like the Bourgain motion and reflecting boundary condition mixes fast. And not only that, there are also other Markov processes like the ball walk and other rapidly mixing Markov chains. And I think that this was maybe the motivation of Chen, and for sure motivations of others like Kannan-Lovasz-Simonovits and Kannan-Lovasz-Simonovits. So the idea is that if you want to have an algorithm that approximates the volume of a convexity in high dimension, one of the ways is to just run some Monte Carlo Markov chain, run some random process and sample a random point from it. And then you can use this sampling, for example, to estimate the volume and other characteristic of the convex set. So the fact that the Poincare constant is large, that we have the KLS conjecture, means that the mixing will be a bit faster. And indeed, one of the corollaries of Chen's work is, I think, better exponents in the best algorithms for computing the volumes of convex bodies. Okay, so this was about the applications. Now, how would you prove it all? What are the proof techniques? So how would you prove isoperimetric inequalities for under convexity assumptions? So first of all, first remark is that it's easier with uniform log concavity. What do I mean? So by uniform, so let me formulate a theorem. But first, I think appears. So this is well, if you're more log concave in the Gaussian, maybe so. I return to this connection with the June Neiman's lectures. More log concave in the Gaussian. So this theorem appears, I think, first in Bourgain Ledoux in '96. But you can say it's related to this Levy-Gromov isoperimetric inequality from 1980. So this is the reference. So so suppose you measure mu on Rn. Okay, I said it's d mu to dx is E2 minus rho in Rn. Okay, if the Hessian and rho is so if the Hessian of rho is non-negative, well, this means that rho is convex, so mu is log concave. Let's assume a bit more, something, a uniform lower bound on the log concavity. Let's assume that rho of mu is at least, this Hessian matrix is always at least T identity for any x in Rn. Okay, so in this case, I would say that you are more log concave than the Gaussian. Okay, so this is true for some T. Such that. Okay, so we're given T, we're given the measure. So this is true, so you're more log concave than the Gaussian. Then psi of mu is larger than, look at it, is what you get for the Gaussian. And the Gaussian, the corresponding Gaussian, where the Hessian equals T times identity, is up to translation, up to normalization, this thing. Okay, e to the minus tx squared, not x squared over 2. Let me try to, okay. This is what you get there. And what you get is root of 2 over pi, so that's some constant, times square root of 1 over t. This is natural because 1 over t is the right scaling here. Okay, so this is true if you're more log concave in the Gaussian. Now, yesterday Radek said that there are 15 different proofs of the isopermetric for the Gaussian measure. I don't know all of them, but there are, I know several. So there are many ways. There is you can use Bourgain calculus. You can use I think transformation measure. I like a lot. I mean, at least easy to remember the Caffarelli contraction. Let me just write it. Caffarelli contraction is the following thing. So apparently there exists a measure preserving transform, a measure preserving map from the Gaussian to mu. Okay, this is a probability, both are probability measures. I normalize both of them. These are okay, need to normalize times 2 pi, I think, over it. 1 over 2. Okay, I will not write minus n over 2. I think yes. Okay. Anyway, these are probability measures, both of them. So there is a measure transportation map, which is a contraction, which is one Lipschitz. And if you have a measure preserving contraction from one measure to another, then the transformation constant is only improving. Okay. There's another method of proof, which is convex localization. Okay, which as we said is due to, so actually it's going back to Payne-Weinberger in the 80s, in the 60s, 1960, and to Gromov and Millman, they did more rigorously in 87. But it was made very easy to use by Lovasz and Simonovits and by the Kannan-Lovasz-Simonovits in 95. And their idea, well, very roughly, is to perform hyperplane bisections. So I'll not fully explain the method of proof, I'll just say a few words about it. So you want to prove an isoperimetric inequality. Okay, this means that you're given some subset A in Rn, and we know from Steinmeier we can look on the case for the measure of phase 1/2, and you want to show that it's maximum, that the boundary measure is at least something. So their idea, so maybe this is your convex set, this is your set A, and their idea is to bisect by a hyperplane. So you find a hyperplane H. This is H. this is the two half spaces, H plus and H minus of the half spaces, determined by this hyperplane, such that if you look at the measure of the set A in each of these half spaces, let's normalize it by the half space, it is again 1/2 for both. Okay, so both for the plus and for the minus. Okay, for both plus and minus. So this means that you separated the big problem into two smaller problems. Now you repeat this process again. You get some decomposition of your space into smaller and smaller pieces, this kind of localized, and somehow you reduce the problem to something which is lower dimensional, and eventually you reduce the problem to a one-dimensional problem. Okay, so I didn't explain much except for the basic idea that you kind of can bisect, you can find this higher plane and bisect and reduce the problem to a somewhat different problem. Okay, so I think that my time is exactly up, 45 minutes, so I'm done.